Okay, so first thing we talked about in this unit, okay, was uniform circular motion, okay, and how it was an object moving at a constant speed, but a changing velocity. That's delta changing, delta-ing changing, okay, velocity. All right. If something's velocity is changing, it's always what? Okay, it's always changing direction, and I'm thinking of a word that starts with A. Accelerating, right. Okay, in order for something to move in a circle, it has to be accelerating where?
Towards the center.
Towards the center. Centripetal acceleration. Okay, there are some multiple choice questions about the principles of uniform circular motion on the unit exam. Okay, so we talked about this, how centripetal acceleration was v squared over r, and that centripetal force is really the net force, so it's mass times centripetal acceleration, which is where we get that mv squared over r formula from. Okay, that is so important for basically every problem in this entire unit. Okay. All right, so definitely expect some multiple choice questions about the principles of uniform circular motion. Okay, then we talked about unbanked curves, okay, and how in an unbanked curve, the force of friction is what provides your centripetal force, and we did a bunch of problem solving related to unbanked curves. Should you expect an unbanked curve problem on your unit exam? I would. Okay, and then right after that, we talked about the other kind of curves, which are banked curves. Okay, those are the ones that we elevate one side of in order to create a normal force that has a component acting back towards the center. So when we bank a curve, it essentially becomes an inclined plane. Okay, and that inclined plane produces a normal force that responds to not only the weight of the car, okay, that's on the corner, but also its inertia pushing against the corner, creating a normal force that is now greater than the force of gravity and has a horizontal component that is directed back towards the center of the circle. Okay? It is that horizontal component that we harness to help create a centripetal force. Okay? You are not going to be asked to derive the formula for a banked curve because that formula is on your formula sheet and is on the front of the test. Okay? But it is tan of theta equals v squared over r times g. Should you expect a banked curve question on your? Yeah, I would. Okay, don't be afraid to ask questions as we go here, guys. All right, so sorry, that was all the derivation. I just went over it again, but you're not going to be required to derive it. All right, then we talked about artificial gravity. So we put people inside a spinning cylinder. Okay, the cylinder spins, their inertia wants them to leave the circle, but the inside of the cylinder prevents it and pushes back against their feet with a force directed towards the center, which feels like gravity and acts as a centripetal force and makes them pinned essentially to the inside of the drum. That's artificial gravity. Okay, so when we talk about artificial gravity, we are simply saying that we want the centripetal force, which is actually not provided by the force of gravity, but provided by the normal force, to feel like gravity. Okay, and thus we get that feeling of artificial gravity. Okay, so that normal force that we were talking about is going to equal the force of gravity, which is m times g, and because it's pointed back towards the center of the circle, it is acting as a centripetal force. Okay, should you expect an artificial gravity problem? I would. We really didn't go over that many different kinds of problems in this unit. So like expect one of each basically. Okay, we did unbanked curves, bank curves, artificial gravity, vertical circles, gravitation, satellite motion, and gravitational field strength. We haven't done that yet. We're going to do that tomorrow. Like, there's your written response, basically. Okay. Okay, after we talked about artificial gravity, then we moved on to vertical circular motion. What's the rule I need to remember for vertical circular motion no matter what part of the circle I'm in?
Centripetal forces in minus forces out.
Exactly. Okay, for all vertical circular motion, Fc equals the forces in minus the forces out. What you'll have to be able to do is draw the free body diagram that indicates which forces are present and which direction they go. That would get you a mark, okay, as essentially givens in your question. All right, so we talked about 3 different positions within the vertical circle. Okay, we talked about going over the top of the vertical circle. When we go over the top of the vertical circle, gravity pulls down, which is towards the center or in. Normal force, if it's present, points out. Is it possible for that normal force to be 0? If it is, how do you feel?
Weightless.
Right, that's the situation of apparent weightlessness, okay, that we talked about in the vomit comet, the plane that goes over the vertical circles, okay. We also talked about how if you go over the top of a hill really fast, you're gonna feel lighter, okay. So things to remember about this part of the circle is that Fn is always going to be smaller than, or maybe equal to, but I can't think of a situation where they'd be equal other than you're not moving, which that's not really a vertical circle anymore. Okay, so in all the situations we're going to deal with, Fn is either going to be smaller than Fg or 0. Okay. All right, one of the other situations we talked about was the top of the circle on the inside. And at the top of the circle on the inside, there is a minimum speed. It is the only position where there is a minimum speed because it is the only position where you could fall. Okay, you can't fall off the top of the vertical circle. You can't fall out of the bottom, okay? But you can fall out of the top on the inside. So you have to go fast enough that you are achieving that minimum speed, okay? And if you are going just the minimum speed, what does Fn equal in that situation?
0.
Right, because you're not pushing on the track. Gravity is keeping you in the circle. Okay. All right. How heavy do you feel if that is true? 3 times your weight, okay? Or how many G's are you pulling? 3. Okay, just little things to remember, wording, okay, stuff like that can come up. Okay, the other point on the circle, okay, that we talked about is the bottom of the vertical circle, where you are always going to feel heavier, okay, than you would in a normal situation. Okay, and that is because here, gravity is pulling out and normal force is pushing in, but it has to counteract not just gravity, but also your inertia, which is going to push harder on the circle and make the circle push harder back, so that is where you will always feel the heaviest. Okay. That ringing a bell for everybody? All right, then we talked about universal gravitation. Okay, so universal gravitation actually doesn't involve circles. It does when it becomes part of satellite motion, but universal gravitation in and of itself doesn't have a circular component to it. It is the gravitational attractive force between 2 objects. And that's the important part of it, is that it is a mutual attractive force between them, not the big one pulling on the little one. Okay? Doesn't matter how different their masses are, they are equally attracted to each other by force. Okay? All right. So that Fg is mutual. Okay, this is Newton's universal law of gravitation. The force of gravity is dependent on mass, the two masses, and the separation distance between their centers. Okay, everybody with me there? All right, which has a bigger effect, mass or separation distance? Separation distance. Why? It's squared, right? There's an inversely exponential relationship. If I double the amount of mass in here, I double the force. If I double the separation distance, it's 4 times less. Okay? It's inversely exponential. Okay, what kind of question did we do for that in class? And I said, gee, I always put one like this on the unit exam. Oh, it makes me feel like it's useless to tell you guys things like this. Earth, moon, sun. And I asked you to calculate what? The net gravitational force acting on the Earth. Okay, and now it's either, it can be that situation where the moon is pulling the Earth in the opposite direction, or it could be the moon is pulling in the same direction. Okay, but it's still a net force calculation. Okay, have a look at questions like that when you're preparing. Okay, so net gravitational force. Okay, after we talked about that, then we talked about satellite motion. Oh, look, see, I drew the picture and I forgot I'd drawn the picture. Okay, so satellite motion. What provides the centripetal force for a satellite?
Gravity.
It is definitely gravity. So if you have a question that involves a satellite, you know you're starting out with this. Okay? But it's big Fg, not little fg. Okay? That's Newton's universal law of gravitation, not m times g. All right, so in a satellite motion question, okay, remember you are looking for those 3 words that will be used to attempt to trick you. Okay? If it says height, altitude, or above the surface, it's not giving you or not asking for the entire orbital radius. Remember that orbital radius is measured center to center. Okay? Okay, so we could have this situation where we were either asked to calculate speed or were given speed of the orbiting body. Or we could be asked to calculate or be given the period instead. If we're given the period, that's where we have to do this, okay? Where we substitute this in for v by squaring it and then simply jamming it into that formula, okay? And remember that when we do that, okay, it looks like this, like what we did on our quiz today, okay? So there would have also been this would have been r squared, and this would have been r on the bottom, so the squared and that r on the bottom cancel because it's mv squared over r. Okay, so when we have all of that, it sets up like this. Which mass cancels? Right, the orbiting mass, the mass of the satellite, because all things fall at the same rate regardless of their mass. Okay, and then the last thing, which we haven't gone over and we'll go over tomorrow, is gravitational field strength. Okay. Gravitational field strength works a lot like universal gravitation. It just calculates gravitational acceleration instead of gravitational force. Okay, so basically it calculates little g instead of fg. Okay, so if I want to calculate gravitational field strength, okay, this would be my formula here. little g equals big G times the mass of the body making the gravitational field divided by r squared. We arrive at this by doing this. Force of gravity equals force of gravity. Well, they better, right? I mean, they're the same thing. So really what we're saying with this situation is this. M times G equals big G times M1 times M2 over R squared, and this is M2. Okay? Because again, all things fall at the same rate regardless of their mass. So what happens to M2? It cancels, and that's where we get this formula from. Okay? So we're saying force of gravity equals force of gravity. That makes this mass irrelevant. Now it calculates the acceleration due to gravity at any point. Okay? Obviously, we know it's 9.81 at sea level on the Earth's surface, but if we were asked about somewhere else, like the top of a tall mountain, and given how far that top of that tall mountain is from the center of the Earth, we could calculate little g as well. Okay? That's all gravitational fields during this. I'll go over it in more detail tomorrow.
So you said you use the mass, just like the, just like satellite motion, you use the mass of like the bigger object.
Right.
Not the one that's.
It's the one that's making the field. The smaller object is caught in the field.
Okay.
So the smaller object cancels because anything caught in that field will accelerate at the same rate. Okay, and we don't have to do Kepler because we've taken that off, so you won't have any Kepler questions. What is going on here? Okay, so you don't have to do any Kepler. Okay, there are 8 written. And there are 15 multiple choice questions. Okay, so on the front page of your test will be useful constants like the acceleration due to gravity on Earth, the universal gravitational constant, the average Earth-Moon distance, the average Earth-Sun distance, the average radius of the Earth, the mass of the Earth, the mass of the Moon, and the mass of the Sun. Okay, those are all going to be on the front page because they're also on your formula sheet. Okay, all the kinematics formulas, all the dynamics formulas, all the energy formulas. Not that you'll use any of them, but they're there. Okay, and then all of the formulas that would be on your formula sheet under circular motion and gravitation. Okay, so all of those formulas are on there, okay, for you to use. And I even put on, because he's such a nice guy, I put on the derivation of FC that uses period. So it's actually on the test. You're welcome. Okay, so in the multiple choice section, there'll be stuff about uniform circular motion. So the principles of uniform circular motion, including banked and unbanked curves. Question about vertical circles, principles of vertical circular motion. Question about universal gravitation. Question about Newton's thought experiment. Satellites. And then again, a bunch of questions in a row about uniform circular motion. So a lot of stuff just about the principles of uniform circular motion. there is no calculation in the multiple choice. There's not a single question that requires you to calculate anything in the multiple choice. Okay, and then as I was saying before, in your written response, unbanked curve, banked curve, gravitational field strength, which is also known as acceleration due to gravity. Okay. Vertical circular motion, satellite motion, universal gravitation, artificial gravity, and a question that could be solved a couple of different ways. That's kind of just thrown in there to, yeah, see how you do with it. All right, so being completely honest with you, I think this test, I almost changed it. And I almost changed it, and then I didn't. And I think it is really weighted in your favor. Okay? You know exactly what's on it. Okay? You know exactly how that you've done questions like what's on there. There's no questions that are a surprise. Okay? I really think that if you prepare well for this test, this is a real opportunity to boost the exam grade, portion of your grade. Okay? Because I know the first two exams were, you know, they were kind of tough, they were a little bit tricky. Okay? This one is not. This one is about as straightforward as you could expect a physics unit exam to be. So it is a real opportunity. Okay? Notice that I have never said this test is easy, because I won't say that. I wouldn't say that that's true. I'd say it's extraordinarily fair, slanted in your direction. Okay? Which means if you prepare well, you could do really well on this and boost your grade. If you go, Coderre said this is easy, and don't study, you'll get owned by it. Okay? And then you'll go, man, I wish I'd listened to Mr. Coderre and studied hard for that test. Okay? So that's why I'm telling you this, is I think if you prepare well for this test, you will be pleasantly surprised. Okay? This unit does tend to be the one people do best in. Because it's pretty short. There's really not much in it. Okay, questions from you guys? Anything you want me to cover in a bit more detail? Demonstrate? Okay, I posted the unit exam review in Google Classroom. I'm going to add this recording to it as soon as class is over, right? But if you click on that, okay. Okay, so this is kind of what we just did, telling you what's going to be on there. Okay, Kepler's law, remember, you're only really going to see multiple choice stuff about Kepler, okay? And that's kind of in satellite kind of terms. And then there's some suggestions for things for you to do to review. Okay, these are the formulas that will be on the front page of your test. And these are old exam questions that you might want to try with the answers, so you'll know if you did them right. Okay, so I would suggest that now might be a good time to try some of those, since I'm here to answer questions if any come up. Okay. All right, so on this question, they're telling me, here's Earth, okay? Here's the satellite, and this distance is 2 times the Earth's radius, okay? So what's the orbital radius? 3 times the Earth's radius, because I have to add the Earth's radius on one more time to get the center to center distance. Okay, so my orbital radius will be 3 times the Earth's radius, which will simply be, okay, 3 times 6.37 E6. Okay, so 1.911 times 10 to the 7. Okay, so there's my orbital radius. Now I've got that. Okay, the masses involved are the satellite and the Earth. The mass of the satellite's not going to matter, okay, but I'm looking for the period of that satellite. So I'm going to say FC equals FG, which is true for anything orbiting something else. And I'm going to say that M times 4 pi squared times R over T squared is my centripetal force. And then on this side, I'm going to have big G times the mass of the Earth times the mass of the satellite over R squared. Okay, so we've already said mass of the satellite is going to cancel. I'm trying to solve for T.
When we say FC equals FG, isn't saying the formula right below it the same thing? So
Yep.
okay, so on like a unit test, you could write either or and be fine. Or do you want to?
Well, I usually I'll definitely give a mark for identifying that this is occurring. I'll give another mark for manipulation. So yeah, either or is fine. Yep. Okay, so I'm trying to solve for T. I've got to move it from the bottom to the top. So it's got to come over here. Then I've got to move everything else to the other side. When I multiply R squared by R, I get R cubed. All right, and then I'm going to divide both sides by big G times the mass of the Earth, and then I'm going to square root. Okay, so big T, the period of the satellite's orbit, is going to be 4 pi squared times 1.911 times 10 to the 7 cubed divided by 6.67 times 10 to the minus 11, okay, which is big G, times the mass of the Earth, 5.98 times 10 to the 24. All right, so when I punch all of that in to my calculator, so square root, bracket, 4 pi squared, 1.911 7 cubed divided by oh no. Struggling here. 5.98. 4. Okay, so I am getting a period of 2.6281.93821. I keep every one of those numbers. Why?
Because there's infinite significant digits.
Right. There are no measured values used in this question. Everything is from your formula sheet, all of which are considered to be absolute. How many dirty tricks are there in that question? A lot. Okay, I had an above the surface. I didn't even give you any numbers. I used Earth radii instead. I asked for period, not speed. Okay, I basically did everything I could possibly do to make that question awful for you. You're welcome.
How many significant figures would we write? Like, would we just go till we ran out of room on our paper?
Well, that only goes to there. So I'd write all of them. Okay. Now you could convert this to hours if you wanted. They're 3,600, right? So we're looking at 7.3 hours. Okay. It's quite a ways away at 2 or 3. All right. What was the other one I was doing? Artificial gravity. Okay, so that would be a artificial gravity question.
I was just gonna ask you what
All right, so here's what we know. We're looking for the radius of the space station. We know that it is spinning at 51 meters per second, and it's producing a feeling of normal Earth gravity. So, Fc equals the normal force, which I want to feel like this force. Yes? So, mv squared over r equals m times g. I want the centripetal force to feel like gravity. So I'm looking for r, so I'm going to multiply both sides by r, okay, and then I'm going to divide both sides by m times g. The m's are going to cancel. R is going to equal v squared over g. Okay, so that's going to be 51 squared divided by 9.81. So it's big. It has a radius of 265 meters. Actually, 2.7 times 10 to the 2 meters, because we only have 2 significant digits. Okay, making sense?
Yeah.
They're a lot easier than they sound when you write them out. Okay, anything else? Okay, well, where did I put it? Right here. Come on. Oh, for some reason I filled out this screen. Okay, so in your review package, which is in Google Classroom, okay, you will see this. Okay, so it starts out with basically what we did. These are the things that are going to be on the test. Okay, some suggested things for you to do, and these are the formulas that will be available to you on your front page of your test. And then these are some old exam problems for you to try. Okay, so I would suggest that doing these might be a good idea right now.